Okay, welcome to Astronomy 405, and we're continuing our discussion on exoplanets, and we're going to talk a bit about what we've learned. So we're going to talk about results and a bit about spectroscopy, and which includes under the results, and showing us a little bit of what we learned in aggregate. So again, with exoplanets, we're not getting a lot of detailed information. One of the easiest things most methods will give us is either the mass or the radius. And if we, for instance, have a transit, we have the radius. If we have either radial velocity or some transit timing variations, we'll have a mass. And transits and imaging are nice as well, because that means we're getting some interaction with the light. And we can do some things like albedo, temperature measure, and spectroscopy. And it's harder to work with radial velocity. You can learn a little bit. A lot of this tends to be focused on the Jupiter-sized planets first, because those are frankly the easiest to see. So let's first start with the overall thing, numbers. I said 4,151 last lecture. And this is a graph for per year. This is also color-coded by method. And you can see there's some, near the top, there's a lot of fuzzy rainbow colors, including, you can kind of see which years were really good for microlensing. But by far, the two methods that are dominating here are radial velocity and transits. Radial velocity has been steady for the last 2 decades, or maybe a little bit increasing. And transits have kicked off in like the last decade or so. You could also see which 2 years the Kepler Space Telescope, which was a dedicated transit or dedicated instrument to detect exoplanet transits. You can see which years it did a major data release. So let's look at the results, radial velocity. Now, I've mentioned it before that some of the first planets we found around sun-like stars are hot Jupiters, which makes sense because if you're looking for radial velocity, what you are going to find first are massive planets in close-in orbits. It's also what you find first for transits. So now, hot Jupiters tended to be solo planets. We didn't see that many other planets close into their stars within the limits of our detection. But with the exception of these hot Jupiters, it seems like planets tend to come in groups, which makes sense. That's the way they do form in our solar system, that the best place to find a planet is a system already has planets. So we found many multiple system groups. Most systems seem to be multiple planet systems. Now, we also, we know from our sun that singleton stars have plenty of planets, or at least they can easily form planets. Binary stars also form planets. One of the first planets we found was around 55 Cancri A, also Gamma Cephei A, which was the retracted planet that came back, that was unretracted. So here's a system called 55 Cancri A. It's showing several of the planets B, C, and F. Now, our custom for naming planets is that they get a lowercase letter after the star's name. So 55 Cancri B was the first planet discovered around the star 55 Cancri. Sometimes for clarity's sake, you will call it 55 Cancri AB. You can also see E is in there, unlabeled, and D is not shown. Now, we call these types of orbits S-type orbits for binary stars. They're orbiting one star. There's another star that's much farther out. You can see these are pretty close-in planets. We got 1, 2, 3, 4 planets inside the Earth's orbit. So we have hundreds of planets we've discovered with the radial velocity method. If we go back to the chart, see we get, several dozens every year. But let's talk about transits. A lot of them are through the Kepler mission. The main mission was from 2009 to 2012. It ended a few years ago. And what Kepler did was the mission stared at one portion of the sky and regularly sampled every star in that section. So it's a very deep search. There's a picture of the telescope, or a drawing of the telescope, and a picture of the region it was surveying. Now, currently, Kepler was replaced by a mission called TESS, the Transiting Exoplanet Survey Satellite. It's another transit survey. This time, TESS samples most of the sky. That's the grid at the bottom is showing how TESS samples. So the grid at the bottom shows what TESS sample is like, and it'll get basically a long strip. Once every 27 days, it'll change strips, and then it'll do one half of the sky, then do the other half. As a result, there's, the top regions, the regions of the sky near the ecliptical poles are getting sampled almost continuously. Regions near the ecliptic are less sampled. And the reason is partially that the James Webb Space Telescope, which will launch in a few years, I hope, will be able to also study that portion of the sky all the time. We're looking out of the plane of the solar system, so it'll be nice and cool. TESS has only found about 45 planets so far, but it also has a long list of planet candidates. Things that look like transiting planets to TESS, but we need to someone needs to go through and basically exclude some of the things that can be mistaken for a transiting planet, like eclipsing binary stars. And this is kind of showing what the big deal with Kepler was. This is a graph of all of the planets discovered by everyone out to 2016. And the blue and the gold are the Kepler planets. You can see, again, they make those two giant spikes in planet discovery because of major data releases. And one of the things Kepler was really good at discovering was transit surveys tend to be very sensitive to planets that are close in, as we explored with the math. The probability of transit is inversely proportional to the semi-major axis. So, and also we have an effect where if we only study a system for a few years, we're unlikely to catch a transit of a planet that's farther out. So what Kepler found is some very interesting systems. Here's Kepler 11, which I mentioned because we looked at it from transit timing variation, and here's TRAPPIST-1. Kepler 11 is surrounded by a star that is roughly sun-like. TRAPPIST-1 is a little red dwarf. And both of these systems are multi-planet systems. Kepler 11 has 6 planets. TRAPPIST-1 has something like 7. And both of them are very, very compact for very large planets. These are all what we consider super-Earths, planets in between Earth and Neptune mass. So they could be kind of mini Neptunes, or they could be super-Earths. And all of them fit very compactly. We fit a bunch of planets, all bigger than the Earth, in a space that for Kepler 11 was inside the orbit of Venus, and TRAPPIST-1 inside the orbit of Mercury. This is a lot more compact than what we thought, and you can kind of see these drawings to scale. Now you can also see that the TRAPPIST-1 star is pretty small. It's a little red dwarf. This aids kind of in transit discovery because while basically it is much smaller, it's small enough that even a small planet will make a pretty substantial blip, block a pretty substantial amount of light. Now there's some other stuff we can do with transits. We've mentioned primary eclipses and secondary eclipses. Primary eclipse is where the planet is in front of the star, or primary transit is when the planet's in front of the star. Measure how big the planet is because it's blocking a certain amount of starlight. A secondary eclipse is when the star is the one in front, the planet's passed behind the star, so we're only seeing the star. Now, one of the things we can do is not just look for those two eclipses. Secondary eclipse tends to be pretty faint. Primary eclipse tends to be like the obvious one. But we can then try to measure what's going on with the planet in between those. Now, in the visible light, we would see the planet going from new during primary eclipse to full right before secondary eclipse. But in infrared, we're measuring the temperature. We're seeing the planet go from the night side to the day side. Now, just like most of the moons in the solar system, this planet's probably tidally locked to its star. It's very close. Transiting planets tend to be very close to their stars. So we're essentially making a temperature map. Now, this is an example. This is WASP 43b. This is an infrared measurement. It had 3.6 microns and 4.5 microns, done with the Spitzer Space Telescope, probably. Now, notice that at the orbital phase, we've just scaled it so that 1 is one orbit. At orbit at 0.5 and 1.5, this normalized flux, we're only seeing the star. That's the secondary eclipse. And you can see at 1, we see the primary eclipse. But we notice that when we're seeing both planet and star, we are seeing a little bit above 1. The planet, we're detecting some of the planet's light, and it's in these wavelengths, it's about a few tenths of a percent. We go from 1.004 to 1.000. And this lets us make a temperature map. We model the planet as a sphere. It's got parts of it are various temperatures. And as the planet rotates, we're going from seeing the night side, which is at primary, to the day side at secondary. So this is another example. This is HD 189733b, or rather the HD 189733 system. And again, primary transit is a few percent. Secondary transit's a few tenths of percent. And in between, there's variation as we go from the cooler night side to the hotter day side. And this lets us make a thermal map of these planets. And now these are all really hot Jupiters. So this tells us, roughly what their temperature is, which is very hot. And it also tells us something about wind speeds. Now notice HD 189733b turned this information about how much brightness we get into a temperature model. And the longitude is set such that the center longitude in this map will be the subsolar point. We're assuming this planet spins once per orbit. It's locked to its star. The orbit's very circular. We assume that the place in the center of that map is noontime all the time. The sun is constantly overhead forever. And the spot at the edges of the map is midnight forever. Now, since this is a Jupiter, there's a big atmosphere. It can carry heat around, so the midnight forever is not terribly cold like it is on an airless body, like it would be on an airless body. But the hottest place on this planet is shifted, which tells us that there's wind speeds here, that winds are carrying heat around so that the hottest place is not right below the sun. It's the star, it is a bit to the west because wind is blowing the hot air to the west. So this lets us make maps. I mean, they're kind of temperature maps, but they're maps. Now, we see secondary transits in the infrared. And that makes sense because these planets are hot Jupiters. They're very, they're close to 1,000 Kelvin. So while they're much cooler than their stars, they're not non-trivially bright. We don't often see secondary transits in the visible. Usually it looks completely boring except for the primary transit when the planet's blocking the star. Kepler 7b is a weird exception though. Again, we can see its secondary transit, which tells us that this planet does reflect some light. The fact we don't see secondary transits for most hot Jupiters tells us they're actually quite dark. They glow they're probably glow faintly red by their own heat, but their clouds don't reflect light like our Jupiter does, which we can then put into our models about how clouds work and what things we expect to find to make some estimates. That these Jupiters don't have clouds in the upper layers because clouds are reflective. But back to Kepler 7b, we take its phase curve and we model it in the visible, and we get that it has clouds. It's just that they're all on one side of the planet. So kind of an image of Kepler 7b. Now these clouds can't be water. This planet is way too hot for water. So these clouds are probably vapor or droplets of silicates. So Kepler 7b not only has this weird cloud pattern, but those clouds are molten rock or tiny rock grains. One of the other things we can do with transits is we can do a few things. During secondary transit, we now have a spectrum of the star without the planet in the way. During primary transit, we can then measure what light looks like when it shines through the planet's atmosphere by comparing it to the secondary transit, which is really hard to do, but if we have data of sufficient precision, you take star plus light shining through planet's atmosphere minus star with the planets behind the star, you can't see its spectrum, and you get a spectrum. And you could also just measure the depth of the transit at different wavelengths. That's another thing you can do, is just say, okay, if this transit is deeper in one wavelength than the other, then the planet's atmosphere is more absorbent. Because remember, these are mostly hot Jupiters. They're mostly atmosphere. And here is an example. This is a transmission spectrum. We're measuring basically the size of the planet with respect to wavelength, which we can do because it's an atmosphere. The size is basically determined by how absorbent the atmosphere is. And the brown point or the black points are data. You can see this planet doesn't vary that much. And the various colors are models. So the orange is what you'd get if you just stuck the sun's atmosphere on this thing. The blue is what you get when you stick water, just 100% H2O. And the green's kind of in the middle. And one of the things you observe is if you look around 890 microns, the no water model, the solar composition model, the planet would look much bigger than the water or the mix of water and hydrogen model. So that tells us this planet probably has a water atmosphere, and it's much closer to a super Earth or a kind of an intermediate object than a mini gas giant. It's not a particularly big planet. It's only about 2.5 times the radius of the Earth. So it's smaller than Neptune, but bigger than we are. So this can be really useful for teasing out what's going on in the atmospheres of the planets. Now we do need these models to compare to. You can see this particular planet, GJ 1214b, is pretty, it's pretty spectrally gray. It's pretty boring. And only the fact we've done these models and compare things to the models lets us kind of figure out, oh, we can rule out some stuff. We can also do spectroscopy with those directly imaged planets. So here's an example with a HR 8799b. And again, usually we also fit a model to this to kind of make sense of it. So black is data, and red is our model. And you can kind of do this with radial velocity. You never get the clean, no star, or rather no planet, here's the planet with radial velocity, but based on the radial velocity curve, where the planet is relative to the star. So if it's a crescent versus a gibbous. So you can kind of tease out features. It's not easy. We've done it with 51 Pegasi b, but we haven't done it to very many planets. So transit makes it much easier. Now the other cool stuff Kepler's found. So radial velocity is pretty early on discovered planets around one star, like in a binary. But Kepler found a planet that circles 2 stars, what we call a circumbinary planet. Sometimes people call all these like Tatooine planets after the planet from Star Wars. So basically, instead of circling one star, this thing is circling a tight binary, 2 stars very close together. This planet is circling their center of mass, and it's roughly Saturn-sized. Another cool thing we can do with transits is if we're doing spectroscopy during the transit, we can notice something about how the star's spectral line changes, because So here's our star, it's rotating. So that means one side is blue shifted, one side is red shifted. That's what we talked about, how that makes radial velocity search. We talked about how that makes radial velocity searches rather challenging because this broadens the spectral lines because part of the star is blue shifted, part of the star is red shifted. That just makes the line look broader to us. But, so let's look at this from a transit point of view. So in this case, our planet is rotating prograde. It blocks first the blue shift side and then the red shift side as it moves towards us and then moves away from us. And if this planet were orbiting retrograde, it would block first the red shift side, then the blue shift side. Now that means that the star's line, the shape of the line will change. We're getting less blue shift in the middle picture. So the line will shift slightly redward and it'll be a little asymmetric and then at the end of the transit, the asymmetry will be reversed. Spots can do this, so you have to be careful and, do this for multiple transits. But it does give us a hint of what is the planet's inclination relative to the star. And, is it orbiting prograde, retrograde, or polar? If we don't see this effect, this Rossiter-McLaughlin effect, that might tell us the planet is orbiting polar relative to the star's rotation. Now, again, all of our planets orbit prograde, but some of the hot, the close-in planets we find with the transits orbit retrograde, and it seems to be more common in hot stars. So it's telling us something about how these things form, because that's really weird. All right, but the big thing we want to talk about is things like sizes and masses. We want to start doing some statistics. So this is another plot of all the planets we know about. I grab all of these when I'm updating the lecture. So this is, again, every planet we know the mass of. Now we're missing a lot of transiting planets that are small because we don't know their masses. We just have limits. And we see a systematic bias. Most of the planets we know about are radial velocity or transit, so that means we mostly find Jupiter mass planets out to maybe Jupiter-like distances, and Neptune mass planets and Earth mass planets very close into their stars. You can also really see that, we don't find that many transiting planets with orbital periods longer than 100 days or so, which is usually just the bias of an observation campaign or just missing the thing. Find radial planets with periods out to maybe 10,000 days. So you can see the region at the kind of where Earth and Venus sit on this graph is pretty empty, and that's mostly due to just observational bias. The region past where Uranus and Neptune, again, observational bias. Those planets take, centuries to orbit, so we don't find that many of them. Also see that why microlensing and imaging can be really important, because microlensing is letting us find planets at Jupiter or Saturn distances, and imaging also lets us see planets farther out, though those are all young planets. But again, if we can get both a transit and some measurement of a mass, either through transit timing or radial velocity, we can start to make a mass radius map. So here is a big busy plot, and I apologize for that. But you can find many variations of this, and I'm going to show you another one on the next slide. So let's walk through it. On the bottom is mass. It's plotted on a log scale. On the side is radius. Both of these are in Earth units. So Earth is sitting at 1,1. You can see it. It's plotted in gray. And there's Venus next to it. Up at the upper right, you can see Uranus and Neptune. And here's a bunch of the planets we have masses and radii for as of a few years ago. Colors are basically their temperatures as an estimate for how hot they are, and all of these are hotter than Earth. They're all close in transiting planets. The purple ones are, maybe possibly habitable. Purple ones might be down at more like Earth or Venus-like temperatures. Now let's look at the lines. The lines are basically the theoretical relationships for mass and radius. So the bottom line is 100% iron. Then we segue up to a mix of iron and rock, and then we have 100% rock in pink. We're using magnesium silicate, and then we add water, mix of rock and water, to 100% water. in blue, and then go up and we get to 100% hydrogen and helium. And we do this as cold. If you heat a gas, it puffs up a lot more. And hydrogen and helium is probably the most gas-like of anything on this plot. Why this is important is if you look, as you can see at like sizes of 4, 5, 10, 20, maybe not out to 20. You can see it sizes from like 4 to maybe Uranus and Neptune's 15. There's a big variation in radius. So there's some of these planets are rocky. Some of them might even be like super Mercuries. They're mostly iron. While some of these planets are more like Uranus and Neptune. They're they're gas giants. Small ones, but gas giants. But as we move to maybe smaller than 2 or 3 Earth masses of planet, most of the planets kind of sit between the water and the iron line. There's some mix of, actually most of the planets sit between the rock and the iron line. There's some mix of rock and iron. They're like Earth and Venus. There's a few exceptions, but it seems to be mostly true. And this plot doesn't show it as well, but as you go out from 20 to 30 Earth masses, most of those planets, you're finding very few rocky planets. This is telling us something about pattern. There aren't very many rocky planets the size of Jupiter. There aren't very many gas giants the mass of Earth. There's some kind of transition between Earth and Neptune. Here's another variation of this plot. And again, I grabbed this one more recently. Here we're still showing planets. We're only going out to about the same degree. Here we have a bunch of lower limits on this plot, which are the arrows. And again, you can see at planets the size of planets that are Earth mass or Earth radius, they tend to be rocky. They're kind of in between the iron and the water line. So they tend to be made of iron, rock, maybe some water. Planets outside of Neptune, which is about 15 Earth masses, are shifting up above those lines for iron and rock. So let's look at a broader picture. So this is from Chen and Kipping, 2016. It was a systematic review of all of the round things we know about in the universe. So it's missing some of the planets. It's missing some of the exoplanets, but good. Now our solar system, the planets are in gold. And so this is a mass on the bottom, radius on the top, or radius on the side. And it goes from 10 to the negative 4 Earth masses. So that would be 1/100 of 1% to 10 to the 6 Earth masses, where we're well into stars. So what this was looking at was basically a general trend for mass and radius over wide scales. And one of the things it observes, you see there's much fewer of the small exoplanets, was that solid worlds, so the planets, our moon, a lot of the icy satellites, the dwarf planets, they tend to fall into a power law where the radius goes as mass to the 0.3, which makes sense. For uncompressible material, the radius should go as mass to the 1/3. So this is saying, well, there's a little bit of compression, but this stuff's pretty solid, so it doesn't compress well. Then from about 2-ish Earth masses to maybe a Saturn. So 100 Earth masses or 1/3 of a Jupiter. Planets are more like Uranus and Neptune. We have a mix of hydrogen and heavier elements, and they tend to have a very sharp relationship between mass and radius. Then you go out from again, about 1/2 a Jupiter to the fusion limit, where we kick on hydrogen fusion. So we have Jupiters and brown dwarfs. We have planets that are all about the same radius. And then, we kick on fusion, we go to stars and have a different relationship between mass and radius, thanks to fusion. So this is telling us something about both composition and internal pressure. And we have good models for how internal pressure works. So this is telling us something about trends of composition with planet size or planet mass. Now, the tricky thing is working out what this is telling us, because if we model everything as having two things, rock, hydrogen, rock, water. If we have the mass and the radius, we can figure out what mix of rock and hydrogen, or rock and water, or hydrogen and water can make a certain thing. But for 3 more ingredients, it's impossible. For instance, you can simulate 100% hydrogen or 100% water world with a mix of rock and hydrogen, because water's kind of in the middle between them. Unless the world is almost 100% rock or almost 100% hydrogen, you can replace some of that rock-hydrogen mixture with water and get a planet of the same mass and same radius. So we can tell if a planet's very rocky or very gassy, but we can't tell anything in the middle, which is a shame, because those are the interesting ones. You know, we want to figure out what are the worlds like Neptune, or what happens if you make Neptune smaller. So how we do this is something called a ternary diagram. These can be confusing, so I'm going to walk you through it. So we have 3 ingredients: rock, or Earth-like material, so it's a mix of rock and metal, water, and hydrogen and helium, so like Jupiter atmosphere. Those have to add up to 100%. So how these are often plotted is as a triangle. Each point on the triangle has a mix of 3 things plotted with it. So each of the corners is 100%. Each of the kind of dotted lines perpendicular to the triangle is then the line of constant material. So the horizontal lines, so the top is 100% hydrogen and helium. The bottom of the triangle is 0% hydrogen and helium. And then you can see the numbers are telling you the percent of water, with the remainder being rock. So the bottom right corner is 100% rock. The bottom left corner is 100% water. Now these can be tricky, you know. This is not the first take of the video I've recorded. It's because you're trying to read basically a graph that has 3 axes that was put into 2 dimensions because you have 3 axes and 1 constraint. You have to add all 3, have to add up to 100. So it takes a while to stare at this and make sense. The main takeaway from this is you can show some trend of how size changes with 3 different ingredient compositions. The hydrogen helium rate fraction seems to be the big driver in planet size. But if you start building your planet of very little rock with just water and hydrogen helium, you get a much bigger planet than if you build it with very little water and just rock and hydrogen helium. And if you stare at these plots too much, you can go cross-eyed, because plotting multiple things, more than 2 things at once, is a difficult challenge. So, all right, we looked at this graph before. Solid planets, you get a little bit of compression, but it's mostly just a matter of scaling. It's very close to the incompressible radius radius goes as mass to the 3rd. In the Neptunian world, you're starting to get planets that are that seem to be going from more like, you know, Earth with a little bit Earth, which has no hydrogen, to Jupiter, which has mostly hydrogen and helium. So the size trend seems to be describing how the composition is shifting. And at about 0.4 mass of Jupiter, is a little bit bigger than Saturn. The size of this object starts going such that if you add more mass, it just compresses more. Hydrogen is, you know, these is a mostly hydrogen and helium body, and hydrogen helium is very compressible. So all of these objects from Saturn to the smallest star are all about the same radius of Jupiter-ish. But here's an interesting thing. Many of the hot Jupiters are too large for just a cool envelope. These planets have been puffed up by something to make them several times the size of Jupiter. And there's been various, we don't understand exactly why. There's various energy sources. We don't think it's just the stellar heating. It might have to do with things like tidal dissipation or all kinds of weird stuff. But hot Jupiters tend to be puffy. So let's talk a little bit about the host stars. Because we want to do these, if we were looking for planets, especially with methods that require detailed study like radial velocity or astrometry, we want to be able to predict which planets are most likely to have stars. Transits and microlensing, we can kind of cast a broad net. But once we find things with those methods, we can kind of try to disentangle what planets host stars are like. First thing we might want to look at is the metallicity. What's the abundance of elements heavier than hydrogen and helium, which we typically measure with iron abundance. So you can see the ratio plotted is Fe/H, iron over hydrogen. And it's normalized, so it's a log scale. The sun is 0. We're comparing relative to the sun. So negative numbers means you have less iron than the sun. You're less iron rich than the sun. Positive means you're more iron rich. Now, one of the interesting things is that we see, when we look at gas giants, you're far more likely to find a Jupiter mass planet, a Jupiter-sized planet, around a more metal-rich star. That's what both of these plots are showing. The left plot is showing the relative frequency of finding a Jupiter-like planet around a star as plotted relative to metallicity. And you can see below about a metallicity of negative 0.75 or so. We just don't see them. The right plot is comparing planets. So this is a histogram of the number of planets we found. The total sample is in blue and it's divided by 10, so it plots on this graph. The black line is showing us the gas giants, and you see there's a lot more around metal-rich planets, while the ice giants and the super Earths, the planets that are smaller than about 30 Earth masses, mostly seem to track the general trend of the sample. So this is telling us that we find Jupiter mass planets more commonly around metal-rich stars, but there doesn't seem to be as strong of a trend for Neptunes and Earths and in-betweenies. That's might be counterintuitive, you might think, but it's telling us something about how you make a Jupiter versus a Neptune or an Earth. So we might want to split. Okay, let's see if we can split a Neptune and an Earth. Let's pick 10 Earth masses as our boundary. The Neptunes are in green, the Earths are in blue. Again, it seems like you're less likely to find a big planet around a metal-poor star. Now, the caveat for all of these studies is that most of the planets we know about are the close-in planets. So it could be that simply that these metal-poor stars tend to have, might still have Jupiters and Neptunes, but they're farther out, like they are in our own system. But certainly an interesting trend that's going to hopefully tells us something about how planets form and how an Earth differs from a Neptune from a Jupiter. These are just all of the planets plotted as planet mass versus metallicity, and showing that we just don't find big planets around metal-poor stars. And again, our sun is 0, so most of the stars in this sample are less metal-rich than our sun. So let's continue on this metallicity trend, because it seems to be really interesting. Something about the mix of ingredients that makes a planet is going to tell us about the type of planets you form. So this is from Dawson et al. In 2015, noticing that for orbital periods greater than 15 days, so we're going to set the other ones aside because they're getting a lot of flux from their sun, and that might be dominating things over the ingredients you make the planet out of. But for periods larger than 15 days, when you look at those intermediate-sized planets between Earth and Neptune, their radii are more likely to be large than small, which tells us they're more likely to be gassy Neptunes than rocky Earths. And again, these are super Earths or mini Neptunes. They're in between Earth and Neptune mass. So you can see this in the plot. Again, on the bottom, we're plotting the period of the planet. On the side, we're plotting metallicity. This time it's a linear scale. We've de-logified it, so the sun is 1 on this plot, because 10 to the 0 is 1. In the gray shaded region, you can see there's some orange Neptune-like planets, black rocky planets, and blue intermediates. But if we look at the pink region, there's very few rocky planets in the size bin. Most of them seem to be gassy Neptunes, at least farther out than 15 days. And again, we're putting the close-in planets, we might assume that the planets might have started as gassy, but the heat from the star might have driven off atmosphere. So what we've learned, gas giants are proportionally less heavy elements, but we're more likely to find them around stars with more heavy elements relative to stars that have fewer. So this is telling us something about planet formation. Something about having heavy elements helps planets grow quicker, because the planet forming disk loses gas before it loses the solids. So this is going to feed into our next discussion, which is planet formation. Now, one more thing we want to talk about is how these planets are interacting. We've talked about the planets on their own. We've talked about how the planets deal with their stars. And now we're going to talk about how planets interact with each other, because now that we've discovered multiple planet systems. And here's an interesting trend we observed. Well, first we've observed that our solar system is widely spaced, but that's not universal. We've observed plenty of systems that are really tightly spaced, like Kepler-11 or TRAPPIST-1. We also observed resonances, and our solar system doesn't really have resonances between planets, so they're really common in moon systems of like Jupiter and Saturn. But we do see resonances and near resonances in the exoplanets. And the interesting thing is we tend to see an asymmetry. So this is a plot from Fabricki et al. 2014. What we've taken is any type of planet pair, so you have two planets in the same system, and plotted what is their ratio of periods. So one would be a Trojan orbit. You have a planet and it has a Trojan asteroid. So this lets us kind of correct for resonances. The top is a histogram. And one of the things you notice that, like, for instance, the 3-2 and the 2-1, is that right before there seems to be a dip, and right after there seems to be a peak in the distribution. And you can try to convince yourself you see it with some of the other histograms. And then the bottom pages just show the individual planets. We're plotting the size of the planet versus their ratio. At least the size of the outer planet versus the ratio. And again, right interior to the resonance, we seem to see a gap, and that's especially apparent for the 2-1. Though you can kind of convince yourself the 3-2 is there. This is telling us something about how these planets interact and form. That being close to a resonance seems to be a bit of a problem, while being slightly outside of it is less of a problem. So conclusions. The universe is really weird, guys. We found a lot of planet systems that are very different than our solar system. And this means that since our solar system formation theories were originally developed for one system, after we started finding planets after the 1990s and the 2000s, when we started finding planets that were very different from ours, we needed to make sure those fit in our system, our explanation for how you make planets. So that's the next place, is we need to take all this stuff we've been learning for the entire term, bring it together to answer the question of where do planets come from. So today we talked about trends in size and mass and radius so that we could tease out what formation was going to do. We observed that metal-rich stars tend to have larger planets, which tend to be relatively metal poor. That might indicate that the limiting factor for making planets is not, at least for making planets around most of the stars we look at is not actually having enough solids. It's possibly a timescale thing. Planets don't tend to be in resonances, but they tend to be slightly outside of them. Next time, we're talking about planet formation, which means we also have to review a bit about star formation.